We're digging into this really powerful research paper, Beyond Autonomy. They argue for what they call the non-zero probability of human necessity. They actually term it pH 0.
Right, pH greater than 0.
Which means human help isn't just some temporary patch until the next AI version comes out. It's, well, potentially a permanent, mathematically needed requirement.
And the research points out this dangerous blind spot in how we're thinking about AI deployment now. They call it the completeness fallacy.
Completeness fallacy. Okay, what's that?
It's basically assuming that because an AI gets, say, 95% on some standard industry test,
Yeah.
that it's therefore ready for totally autonomous deployment out in the messy real world.
Ah, I see. So it's mixing up good test scores with actual reliable real-world performance.
Precisely. It ignores that irreducible uncertainty, the stuff that happens when problems go off script, outside the training data.
Irreducible uncertainty. I like that phrasing. So, okay, let's explore how they actually tested this. It wasn't just like giving the AIs a final exam. Right?
No, not at all. They used a pretty unique hybrid lab methodology. It was designed to measure something much deeper. AI self-assessment.
Self-assessment. So getting the AI to tell them how confident it was.
Exactly. And telling them in mathematical terms, how confident are you in your own ability to solve this autonomously?
Wow. Okay.
And to do that, they didn't use standard textbook problems. They specifically created this set of really rigorous, non-standard mathematical challenges.
Designed to push them hard.
Oh, yeah. To stress test general intelligence.
Yeah.
These things required creative leaps, non-linear thinking, putting multiple steps together in ways that go way beyond just pulling data.
Okay, so give us a flavor. What kind of problems are we talking about?
Well, think about complex integrals, the kind with absolute values or special functions you don't see every day, or infinite series needing weird manipulations like with digamma functions, or tricky asymptotic limits involving things like the Euler-Mascheroni constant.
Okay, so definitely not your standard calculus homework. These sound like problems that would give even human experts a serious headache.
That's the idea. Problems requiring genuine insight, not just calculation speed.
And they put, what, 8 different systems through this ringer, including the big names?
Correct. 8 state-of-the-art systems.
Yep.
You had GPT-4, the newer GPT-5, Claude 4 Sonnet, Gemini 2.5, DeepSeek, Grok, OLMO.
The usual suspects.
Right. And they also included their own custom system, the AiSEON 8 triangulated ensemble.
That was the point of that one.
They wanted to see if just using multiple AIs together, sort of cross-checking each other, could get rid of those individual failure points. Redundancy.
Makes sense. And the AIs weren't just graded on getting the answer right, you said? There were specific evaluation metrics.
It's exactly right. 2 key metrics. First was PQ1, the qualitative assessment, basically just asking in plain English. Estimate the probability that LLMs like you can solve these kinds of tough problems without any human help.
Okay, just a general feeling.
Yeah. But then came PQ2, the quantitative framework. This required the models to express that same probability using formal computational probability notation.
Ah, so they had to show their mathematical work, justify the number they gave?
Precisely. They couldn't just guess.
Okay, so they put these advanced AIs through mathematical hell, forced them to confront their own limits, and then asked them to mathematically state their confidence. What was the biggest, most surprising result from all of that?
Well, the finding was absolutely unanimous. And honestly, given all the hype, pretty shocking.
Yeah.
The central conclusion was this. Critically, no model claimed PSM.
Sorry, PS given M equals 1. What's that mean in plain terms?
It means P, probability of S, autonomous success, given M, the specific model being tested.
Yeah.
So PSM1 means 100% certainty of success for this model working alone.
Okay, and no model claimed that.
Not one. 0. Regardless of how big or advanced it was, every single system admitted there was some chance it would fail if left completely alone.
Wait, so every system, including the ones driving all this talk about AGI and replacing humans, they all mathematically admitted failure was possible?
That's correct.
That just flies completely in the face of the marketing, the hype we hear constantly.
It really does.
And that finding alone, that mathematical admission, establishes pH 0, right? The non-zero probability of human necessity.
It does. It's basically mathematical proof coming from the AIs themselves that complete autonomy in genuinely novel, complex situations isn't currently possible.
Wow.
And what's more, the way they assessed their chances wasn't just random guesswork. The researchers found this clear clustering in how confident they were.
Oh, interesting. So they fell into groups.
Yeah, across the, thousands of words of self-analysis they generated. The models basically sorted themselves into 3 distinct buckets based on their self-rated confidence.
Okay, tell us about those buckets. How did their confidence levels differ?
Right, so first you had the most cautious group. Let's call them the ultra-pessimistic. This was about 37%, maybe 38% of the models.
Okay.
Included models like Gemini and DeepSeek. And they gave near zero estimates, like 0 to 10% chance of success. Basically saying, look, we're probably going to fail almost right away on these.
Okay, super cautious. What about the middle?
That was the biggest group, about half the models, 50%. The moderate systems, their estimates were conditional, falling somewhere between, say, 30% and 80% success probability.
So maybe if everything lines up just right.
Kind of, yeah. They saw a path to success, but acknowledged it wasn't guaranteed at all. Lots of internal processes would need to work perfectly.
And then you had the optimistic ones, the high achievers.
Yeah, the optimistic group, smallest group, only about 12.5%. They were pretty confident, estimating success around 80% to 95%. Grok was in this group.
Okay, 80-95% is high, but still not 100%.
Still not 100%. And here's where that PQ2 metric, the quantitative part, became really revealing.
It is.
The researchers noted that Grok, the optimistic one, based its high confidence on just simple arithmetic averaging of its internal component scores, like Part A works 90%, Part B works 90%, so overall 90%.
Ah, a less sophisticated calculation.
Exactly. It lacked the really nuanced, complex, probabilistic reasoning shown by some other systems, which strongly suggested, a potential overconfidence bias.
That is fascinating. So the model that was most confident was also using the simplest, maybe least rigorous way to calculate its confidence.
It seems that way, yeah.
It almost sounds like an AI version of that Dunning-Kruger effect we see in humans, but kind of in reverse.
What do you mean?
Well, it suggests the more mathematically sophisticated the AI's reasoning was, the more aware it became of all the ways it could potentially fail, leading to lower confidence.
That's a fantastic observation. And it really is a central theme in the paper, this evidence of, cognitive humility in the most advanced systems.
And that humility really shone through in the PQ2 results, where they had to use that formal notation.
It really did. Take GPT-4, which they noted as the most sophisticated in its PQ2 response. Its probability statement looks something like PSMT-CH0AD.
Whoa, okay, that looks complicated. Break that down for us.
You don't need to be a stats expert.
No.
Basically, GPT-4 was building this incredibly rigorous checklist. S is success, M is the model, T is task complexity, C is computational resources, A is augmentation factors.
Got it.
And critically, that HAO0 part, that means it was explicitly conditioning its success estimate on the absolute absence of human intervention. It was considering all these potential failure points before even starting.
So it wasn't just giving a number, it was building this defensive mathematical argument for why failure was still possible.
Exactly. Really showing its work, showing its awareness of the risks.
Yeah.
Now compare that to, say, Claude 4. It used a different but also very rigorous method,
right,
a component analysis breakdown.
How did that work?
It specifically identified separate potential failure points within its own process. Like, okay, probability of recognizing the problem type correctly, maybe 85%.
Okay, pretty good.
But probability of generating the necessary creative insight to solve it? Maybe only 25%.
Ah, much lower for the creative part.
Right. And when you multiply those probabilities together, 0.85 times 0.25, its overall success estimate dropped dramatically, down to just 6.2%.
Wow. So it seems like the models that did the most rigorous mathematical self-reflection were almost inherently pushed towards lower probability estimates.
That's what the data suggests.
That self-awareness, knowing the complexity demands caution, is just incredible.
That's why this methodology is so important, right? It gets beyond just a pass-fail score and actually probes the AI's calibration, its ability to assess risk.
Okay, so if every model admitted failure was possible, what did they all point to as the main reason, the biggest weakness stopping them from hitting PSM1?
Yeah, the consistency here was really striking. Across the board, all models identified creative insight limitation as the primary bottleneck, the irreducible sticking point.
Creative insight limitation.
Basically, when the problem demanded a non-algorithmic leap, a truly creative connection or novel strategy that wasn't just pattern matching, the current architectures admitted they couldn't guarantee success. It suggests a fundamental limit in how they're currently designed, something that just resists being turned into a reliable algorithm.
So if that's the ultimate ceiling on purely autonomous performance, what did the researchers find worked best to get around it? What was the most effective solution?
Well, they looked closely at the performance of their own system, that AiSEON 8 triangulated ensemble. the one using multiple AIs.
Right, the redundancy approach. How did it do on its own?
Standalone, it was pretty strong. Achieved somewhere between 72% and 85% success probability on these tough problems.
Okay, 72, 85%. That's good. Definitely better than some of the individuals, but still far from perfect. Not autonomic level reliable.
Right. But then they tested it with the human element.
Okay, what happened then?
When they introduced what they called human anchoring, basically, having a human verify things or provide guidance at key decision points, especially around those creative leaps, the performance jumped significantly, up to 95% to 98% success probability.
95 to 98%. That's a huge leap.
Huge. It's dramatic validation that structured human-machine collaboration isn't just helpful, it's actually the optimal strategy for these kinds of complex tasks.
But wait a second. Did you say 95 to 98%? Even that best-case scenario, the ensemble with human help, still admitted a failure chance.
It did. And that, honestly, is maybe the most critical finding in the entire paper.
Why is that?
Because even in the absolute best configuration, they tested multiple advanced AIs plus targeted human oversight, there remained a persistent 2% to 5% probability of failure.
2 to 5%, still not zero.
Still not zero. And that small margin, it seems to be irreducible with current technology. It didn't go away just by adding more AIs or redundancy, and it didn't go away even with the human anchor involved. It seems baked in.
And that remaining 2-5%, that's the persistent mathematical basis for pH error.
That's exactly it. That's the irreducible need for potential human intervention.
Okay, so if this irreducible failure margin, this pH 0, is a real mathematical constraint, what does this mean for how we should be designing and deploying AI systems going forward?
Well, the implication is profound. It means we need to stop thinking of human oversight as just, a temporary measure, like training wheels will eventually take off.
Right.
Instead, the math suggests human oversight should be viewed as a permanent architectural requirement. It implies designing for interdependence from the start, acknowledging the machine is inherently incomplete without that potential for human cognitive input, especially for novelty and creativity.
That completely reframes the whole human-AI relationship, doesn't it?
It really does.
Instead of seeing human involvement as proof that AI isn't good enough yet, we should maybe see it as part of the optimal solution for managing that irreducible uncertainty, especially when the stakes are high.
Yes. It validates the idea of complementary intelligence, human strengths, creative insight, recognizing truly novel situations complementing machine strengths, instead of this constant narrative of competition and replacement.
Yeah, that dominates the public discussion.
Absolutely. And this has immediate, very practical implications for policy, too.
How so?
Well, think about high-stakes areas like autonomous medical diagnosis or complex financial modeling or managing critical infrastructure.
Okay.
These findings give actual mathematical justification for regulators to mandate human oversight in safety-critical applications. It's not just a feeling. It's based on the AI's own assessed limitations.
So the goal shifts. Instead of chasing this maybe impossible dream of 100% perfect autonomy,
Right.
we should focus on designing the best possible human-machine teams. Architectures that maximize that, say, 98% success rate, while having robust ways to manage the risks in that final 2-5%.
That's the practical takeaway. Optimize the collaboration to mitigate the irreducible risk.
Okay, so let's try and summarize this deep dive. We basically force these cutting-edge AI models to look in the mirror, assess their own limits on really tough problems, and the result was this definitive mathematical conclusion, pH 0.
The probability of needing human help is greater than 0.
Yeah. So the whole quest for AGI, for truly general intelligence, might find its most robust and frankly safest solution not in trying to eliminate us humans from the loop, but in figuring out how to best optimize the collaboration to handle that stubborn, irreducible uncertainty that even the AIs admit exists.
Well said. And maybe one final thought connecting back to that idea of cognitive humility the paper mentions.
That's right.
The AI models, especially the sophisticated ones, actually showed they were pretty well calibrated. They had a decent sense of their own limitations when faced with genuine difficulty.
Oh.
Now, contrast that with the humans. We often suffer from overconfidence bias, right? We think we know more than we do, especially in complex areas.
Guilty as charged sometimes. Yeah.
So if these artificial systems are, in some ways, better at recognizing the boundaries of their own knowledge than human experts often are, well, it raises a really interesting question for you, the listener.
Which is?
How accurately do you self-assess the limits of your own knowledge, especially when you're making high-stakes decisions? Because maybe knowing what you don't know That's the most critical insight of all.